Greetings and welcome to the SASMO 2020 walkthrough Part B for Secondary 3 students. SASMO stands for the Singapore and Asian Schools Math Olympiad. All in all, there are 25 questions in total. The first 15 questions are multiple choice questions. You get 2 marks for each correct answer, but you lose 1 mark for any wrong answers. Leaving a question blank earns you no marks. In this video, I'll be going through questions 16 to 25. Answers for these questions come in the form of 4-digit numbers. You get 4 marks for each correct answer. Let's begin with question 16. Find the value of the following expression: 11 square minus 12 square plus 13 square minus 14 square, and so on and so forth until plus 101 square. Pause the video here and give this question a good try. Now, to tackle this question, we're going to do a bit of shuffling of the terms. I'm going to swap the order a little bit. So I'm going to first leave 11 square alone, but I'm going to swap the order of 13 square and minus 12 square. I'll shift 13 square in front and minus 12 square behind. Similarly, 15 square goes in front, minus 14 square goes behind, and so on and so forth. Now you'll see that I get 13 square minus 12 square, 15 square minus 14 square. This is a difference of square, so we can use the difference of square formula. A square minus b square equals to a minus b times a plus b. So using that formula, I'll get 121, which is 11 square, plus 13 minus 12 times 12 plus 13. Notice that 13 minus 12 is equals to 1. For the next set of terms, 15 square minus 14 square gives us 15 minus 14, which gives us 1, multiplied by 14 plus 15. Now if I simplify this expression, I now get 121 plus 12 plus 13 plus 14 all the way to plus 101. This is an arithmetic progression consisting of 90 numbers. So we can use the AP formula. We'll take 121 plus 90, which is the total number of terms, open bracket the first term 12, plus the last term 101, divided by 2. In total, this gives us 5,206. Question number 17. How many digits are there in 5 to the power of 2020 times 4 to the power of 1010? Pause the video here and give this question a good try. This is a pretty straightforward question. First, we'll take the 4 to the power of 1010 and we'll change it to 2 to the power of 2020. Now that we have the same powers, we can group the base together. So we'll get 5 times 2, which is 10 to the power of 2020. This is a 1 followed by 2020 zeros. So altogether, we'll get 2021 digits. Question number 18. The 6-digit number, which is the concatenation of 2x3y72, is divisible by 66. Find the value of x plus y. Pause the video here and give this question a good try. Now for a number to be divisible by 66, that number must be divisible by the prime factors of 66, which are 2, 3, and 11. So the divisibility test for 2 here, it's a bit redundant since the last digit is already even. This 6-digit number will always be divisible by 2. So let's check the divisibility test for 3. The divisibility test for 3 states that the digital sum, which is the sum of the individual numbers 2 plus x plus 3 plus y plus 7 plus 2 is a multiple of 3. So we need to note that for it to be divisible by 3, 2 plus x plus y must be divisible by 3. We'll park this one side first. Let's look at the last one, the divisibility test for 11. This one states that the alternating sum of the digits, which is 2 minus x plus 3 minus y plus 7 minus 2, has to be divisible by 11. If you simplify that expression, you get 10 minus x minus y. For that to be divisible by 11, 10 minus x minus y has to be exactly equals to 0. That means x plus y is equals to 10. And that is all we need. We don't even need the divisibility test for 3 because the question only asks for x plus y. Question number 19. Take a 2-digit number, multiply its digits, then multiply the digits of the obtained product and continue the process until you get a 1-digit number. How many 2-digit numbers will produce 0 at the end of this process? Pause the video here and give this question a good try. So the trick to this question is to work backwards. What 2-digit numbers can produce 0? So the only way two numbers can produce 0 is if one of the numbers is 0. And since it's a 2-digit number, the second digit has to be 0. And altogether, there are 9 such numbers, 10, 20, 30, all the way up to 90. You can see that, for example, 70, you'll do 7 times 0, which gives you 0. So already we have 9 such numbers. But let's think again. What numbers can we multiply together to produce 10? 2 and 5. So that's 2 more numbers, 25 and 52. Both of them, the product of their digits, will give you 10. What about 20? Well, that can be 45 and 54. What about 30? That can be 65 and 56. And lastly, 40. That can be produced by 85, which is 8 times 5, or 58, 5 times 8. Now let's think another step backwards. What numbers can we multiply together to produce 25? Well, 5 times 5. What about 52? None there. 45? Oh, there are a few ways there. You can use 95 or 59. 5 times 9 gives us 45. What about 54? Well, that could be 9 and 6, or 6 and 9. So that's 2 more numbers. And the last one that has a possible outcome is 56. That could be 7 times 8, which can be represented as 78 or 87. So all in all, we have 9 plus 8 plus 7, which is 24 possible 2-digit numbers. Question number 20. Find the value of bracket a plus 2b, close bracket, open bracket, 2b plus 3c, close bracket, open bracket, a plus 3c, close bracket, plus 6abc. And you're also given that a plus 2b plus 3c equals to 0. Pause the video here and give this question a good try. Now I'm going to show you 2 ways to solve this problem. The first way, you need to know a very special algebraic identity, which goes like this. X plus y times x plus z times y plus z is equals to x plus y plus z times xy plus xz plus yz minus xyz. In this particular question, x is equals to a, y is 2b, and z is 3c. So if we sub those values in, we get as follows. Notice that our expression that we want, we have a plus 6abc on the left-hand side. So just nice, we'll bring the minus 6abc over to the left-hand side. And since the left-hand side is now what we want to find, the right-hand side is easy to evaluate. Since we know that a plus 2b plus 3c, that red term is 0, and 0 times anything will give us 0. Now this approach is a bit challenging because you will need to know this special identity. Is there another way for us to solve this problem? Why, yes, there is. There is another way to solve this, and it's a really silly approach. In this approach, we're just going to assume that a, b, and c are all equals to 0, because 0 plus 2 times 0 plus 3 times 0 gives us 0. And if we assume that a is 0, b is 0, c is 0, and we sub that all in, we're going to see that we'll still get 0. Now that's quite a silly answer. What if we try and test with another set of numbers? We could also try a equals to 1, b equals to 1, c equals to minus 1, because 1 plus 2 times of 1 plus 3 times of negative 1 also gives us 0. You can slowly try and sub these values inside the expression, and you'll see that everything will cancel out nicely and you'll also get 0. Question 21. Given that the polynomial function px is equals to x to the power of 5 minus 2021 x to the power of 4 plus 2021 x cubed minus 2021 x squared plus 2021 x minus 1, what is the value of p 2020? Pause the video here and give this question a good try. Now these numbers are pretty big, so we're going to make some substitution. We're going to let a equals to 2020, therefore a plus 1 is equals to 2021. So PA, which is what we want to find, is equals to a to the power of 5 minus a plus 1 times a to the power of 4, plus so on and so forth. We can expand these terms easily. We'll get a to the power of 5 minus a to the power of 5 minus a to the power of 4 plus a to the power of 4 plus a to the power of 3 minus a to the power of 3, and so on. You'll see that all the power 5, power 4, power 3, and power 2 terms, they'll cancel each other out. And all that's left is a plus 1, which is 2021. Question 22. In the following cryptorhythm, all the different letters stand for different digits. Circle plus circle plus circle equals to sphere. Find the value of the sum of the digits sphere, s plus p plus h plus e plus r plus e. Pause the video here and give this question a good try. Now the trick to solving a cryptorhythm is just trial and error. We're going to look at the ones column first. So we have e plus e plus e giving us an e. So we could try e equals to 1. 1 plus 1 plus 1 doesn't give us 1, so that's wrong. Try 2. 2 plus 2 plus 2 doesn't give us 2. And we can keep trying 3 all the way to 9, and you'll see that there's only one thing that will work, and that is 5. 5 plus 5 plus 5 gives us 15. So we're going to carry over a 1 into the tens column. That also tells us that the e in the hundreds column is also a 5 there. So let's start guessing another letter. Let's start guessing the C. We could guess C equals to 1. So if the C is equals to 1, that would mean that we need to carry over a 2 from the tens column to the hundreds column. So there's no reason to eliminate this. Now let's try other possibilities. If you consider 2, 2 doesn't work because in the hundreds column, for 2 plus 2 plus 2 to give you 5, you need to carry over a 9. That's impossible. What about 3? 3 would mean that you need to carry over a 6. And if you want to guess 4 and above, that's not possible because in the first column, 4 plus 4 plus 4 is going to exceed the single digit s that we have in the sphere. So the only possibility is for C to be equals to 1. So now that we know that C is equals to 1 and that we have to carry over a 2 from the tens column, we also know that L needs to be pretty big. In fact, the smallest that L can be is 7. So let's try what would happen if L is equals to 7. Then the R is equals to 2. That means the 1000 column will have 2 plus 2 plus 2 giving us 6. Then we can guess for the I's. I could be zeros. Nope, that doesn't work. I's could be 3's, the remaining numbers. That doesn't work either. It will have a contradiction. We could guess 4, but that would P will become 2, and that's a contradiction. We can guess 8, but that will contradict because the S would have to be 5, which is a repeat. And lastly, if we guess 9, the P would be 7, which would contradict the tens column. So that tells us that the tens column, the L cannot be 7. So we need to guess the next number. So could L possibly be 8? So if L is 8, that's a very short problem because 8 plus 8 plus 8 with a carryover of 1 is 25, and that contradicts the ones column already. That must mean that L is equals to 9. So 9 plus 9 plus 9 plus a carryover of 1 is 28. So we'll bring the 8 over to the R's in the thousands column. We'll have 8 plus 8 plus 8 equals to 24. So we carry over 2 to the tens thousands column. Now we need to guess for I, S, and P. Now, I can be 0. It will work. 0 plus 0 plus 0 with a carryover of 2 will give us the 2, and the S will be 3. If we just add up all the digits for sphere, which is 3 plus 2 plus 4 plus 5 plus 8 plus 5, that will give us an answer of 27. Question 23. In how many ways can the vertices in the diagram below be colored with 3 colors such that any 2 neighboring vertices are not colored with the same color? Pause the video here and give this question a good try. Let's solve this problem by studying the vertex right in the middle, just above the triangle. Now this vertex could be red, it could be blue, or it could be green, 3 possible colors. So let's say that there are 3 ways to color this vertex. Now if we look at the rest of the triangle, assuming that the vertex above is green, there's 2 possibilities for the other 2. It could be colored blue in this vertex and red in the other, or the other way around. So for each color in the vertex where the green color is, there's 2 more possibilities for coloring this triangle. So we'll just put a times 2. Next, let's look at the vertex on the right of the green vertex. There's 2 possibilities there. It could either be red or it could be blue. So for every color that the green vertex is, there's 2 more possibilities for the vertex on the right. So we put another times 2 there. Now there's 4 more vertices coming out from that new vertex, and each of them has 2 possibilities. For example, it could be green followed by blue, red followed by green. There's only 2 possibilities for each vertex, so we're going to times 2 to the power of 4. So we've settled the majority of this diagram already, so we're only left with the left-hand side. But the tricky part is the rhombus on the left-hand side. There are 2 scenarios that we need to consider. In the first scenario, the 2 adjacent vertices to the green vertex on top of the triangle are differently colored. For example, it could be red and blue, or vice versa, blue and red. But in either case, the last remaining vertex on the leftmost would definitely be the same color as the top of the triangular vertex. So if that was green, the leftmost vertex will also be green. This is assuming that the adjacent vertex is differently colored. So we're going to put there times open bracket 2. But we need to consider the other case. The other case is where those 2 vertices are the same colored, which is either both red or both blue. In either case, the last vertex would have 2 possibilities. Like in this case, it could be green or it could be red. So we need to add 4 more scenarios in the case where the 2 adjacent vertices are the same colored. Altogether, if we multiply this out, we would get 1,152 possible ways that this diagram could have been colored. Question 24. Let the first term t1 equals to 1. Let the second term t2 equals to 1 plus 1 over 1. t3 equals to 1 plus 1 over 1 plus 1 over 1. In general, the nth term is equals to 1 plus 1 over the previous term, tn minus 1. It is given that tn can be expressed as a fraction in its simplest form, where tn is equals to pn over qn, and pn, qn are positive co-prime integers. How many numbers among the p's, p1, p2, p3, all the way to p2019, are odd? Pause the video here and give this question a good try. Now, this question looks very scary, but actually has a very simple answer. Let's just list down the terms one by one. t1 is equals to 1, so that's 1 over 1, so p1 equals to 1, which is an odd number. t2 is equals to 1 plus 1, which is 2 over 1, so p2 is even. t3 is equals to 1 plus 1 over 2, which is equals to 3 over 2. So P3 is equals to 3, which is odd. Let's keep going. T4, when you work it out, P4 will be equals to 5. T5, you'll get 8 over 5, so P5 equals to 8. Now at this point, you should start to suspect there seems to be a pattern. Odd, even, odd, odd, even. Maybe it's going to keep repeating odd, odd, even. But if you look even deeper, there is another pattern. 1 plus 2 is equals to 3, 2 plus 3 equals to 5, 3 plus 5 equals to 8. This is just the Fibonacci sequence. So we can test it out. T6 is equals to 13 over 8. So P6 equals to 13. That's the next number in the Fibonacci sequence, which is odd. And you can suspect that this pattern is going to continue forever. All in all, 1/3 of the numbers will be even because it's going to follow an odd, even, odd pattern. That means that the number of odd terms would be 2/3 of 2019, which is 1,346 odd numbers. Final question, question 25. In the diagram below, there are 6 touching circles with centers A, B, C, D, E, and F. It is given that ABCDEF is a regular hexagon and the length of the segment AB is equals to 4. PQR is a triangle such that each of its sides touches 3 of the circles. Find the length PQ squared. Pause the video here and give this question a good try. Problem by labeling the radiuses of the big circle and the small circle. For the big circle centered at B, I'm going to use a red line labeled capital R to represent the radius. For the small circle centered at A, I'm going to use a blue line labeled with a small blue r to represent the radius. Since AB equals to 4, big R plus small r equals to 4. Next, I can color this yellow right triangle with a hypotenuse of 4. Notice that the angle here is 60 degrees. That is the exterior angle of the regular hexagon. 60 degrees is a special angle, so we can find cosine 60 degrees to be equals to half. And that will be equals to the adjacent, which is big R minus small r, divided by the hypotenuse of 4. That tells us that big R minus small r is equals to 2. We can solve this pair of simultaneous equation to get big R equals to 3 and small r equals to 1. I can find the length of this green opposite side to be 2 root 3. I can then construct another right triangle colored here in blue. You can see that this angle is also equals to 60 degrees. And by virtue of the AA test, this blue triangle is similar to the yellow triangle. So using a scale factor of 3:2, we can find that the green opposite side here for the blue triangle is 3 root 3. This tells us that the length of PQ, which is equals to the length of PR for this equilateral triangle, is 2 times the sum of those 2 green sides. So it's 2 times of 2 root 3 plus 3 root 3, giving us a total length of 10 root 3. The question asks for PQ squared, so when we square PQ, that will give us a final answer of 300. Of the SASMO 2020 walkthrough Part B. Stay tuned for the next episode where I'll cover Part A, which will be the first 15 MCQ questions. Thank you for sticking all the way through to the end, and have a great day of learning.